First off, I would like to thank the Astronomical Society of India for presenting me with this award for many reasons. It's obviously great to be recognized for one's contributions to a field, but it's also very special for me to be receiving this by India, in India, my motherland, but also a culture with a great heritage in astronomy, and a tremendous surviving history of intellectual pursuit itself. Okay, there are very few countries that can claim that, and I'm really proud of it. I always like to start on a philosophical note for exoplanet science. For centuries or even thousands of years, we as a civilization have been looking for planets outside the solar system, right? Asking the fundamental question, is there life anywhere else beyond just Earth-based life? And for thousands of years, we didn't know the answers. We didn't even know if there was any planet, if there were any planets outside the solar system, just about until 20 years ago, okay? But 20 years ago, roughly 20 years ago, when the first planet around a sun-like star, outside the solar system obviously, was discovered, it was something like this. Now, this is not real imagery, okay? This is a graphic illustration of a hot Jupiter. There is a sun-like star and a planet going around it. And what we found, the characteristics of the planets really startled us, really changed our whole perspective of what planets should be like. So this was the hot Jupiter 51 Peg B, discovered in 1995 by Mayer and Coulomb. What we found was a Jupiter-like planet. Jupiter in the solar system sits at 5 astronomical units. And now this is a Jupiter-like planet, the biggest planet in the solar system, sitting about 100th of the distance Jupiter is from the sun. Okay, sitting at about 0.05 AU. That's 10 times closer to the sun than Mercury is to our sun. Okay, that's incredible. If you know anything about how planets form and so forth, you will know that there is no theory in planet formation that can explain the formation of such planets in situ at those locations. Okay, so all those theories that we had for 100 years don't apply to these systems, and this is just the first system that we found. And fast forward 20 years. Today, we even know of planets that are sitting in the habitable zones of their host stars. Okay, these are planets that can have liquid water on them. So that's the exponential progress we have made in just about 20 years, starting from a planet which we have no clue about how it can be formed, to planets that are sitting in the habitable zones around their stars at the right temperatures and so forth, to even have liquid water, and for all we know, may also host life on them. We just don't know if they do. Okay, so that's when we say about exoplanets being the most rapidly advancing field in modern astronomy. This is what we mean. The progress is really exponential. It's not just in the characteristics of the planets that we are observing, it's also in the numbers of the planets that we are observing. We know today of thousands of these planets around other stars. Okay? Now, one key metric, just to give you a sense of the diversity out there, one key metric, if you look at the sizes in the solar system, planets are roughly quantized in sizes. There are 3 size ranges. The terrestrial planets of the order 1 Earth radius or smaller. Then there are the ice giants, which are of the order 4 Earth radii in size. And then there are the gas giants, Saturn and Jupiter, which are between 8 and 10 times, roughly, of the order 10 times Earth radius. So for the longest times, all our theories of formation of these planets catered to this quantization in the sizes. Of course, when exoplanets came in, today we know thousands of these planets, there is no quantization. Fundamentally, there is nothing in nature that says that planets cannot be formed in sizes between these sizes that we see in the solar system. Okay, so that already, just by detecting the planet, already is a revolution in our understanding that there is no particular quantization in sizes. Planets can come in all sizes and masses. Now, that also brings a host of questions. What are these planets like, which are in between Earth and Neptune range, Neptune size, and what are these planets like between Neptune and gas giants? The last 20 years have taught us 2 very basic points. One, that exoplanets are extremely frequent. Okay? Exoplanets are out there, ubiquitous in nature. They're everywhere. So when you see in the news of statements like there are 1 trillion planets or 1 billion planets in the galaxy, this is what they mean. These numbers, if extrapolated to the population of the galaxy, gives you hundreds of billions of planets, okay? Planets are ubiquitous. That's number one. The number two key point we have learned is that exoplanets are extremely diverse in their macroscopic parameters. Their mass, their radii, I showed you how they have all sorts of radii, but they're also extremely diverse in their masses. They can have masses anywhere from Earth size to Jupiter, which is 300 times the Earth. Not just the mass and radii, they are also extremely diverse in their temperatures, okay? Just their equilibrium temperatures, which can be calculated very easily just based on the distance from the star, okay? So here's a cartoon that shows that all the solar system planets are down in this innocent corner. Venus is by far the hardest with about 600-700 Kelvin temperatures, and Jupiter is cold and so forth. But exoplanets have temperatures of up to 3,000 Kelvin, okay? To give you a sense of what 3,000 Kelvin means, iron melts and vaporizes at 3,000 Kelvin. So imagine Jupiter with iron vapor in its atmosphere. So if you were sitting on an Earth-like planet at 3,000 Kelvin, you would be breathing iron vapor. Okay? So these are the kinds of planets that are out there for which we have no concept of what they should be like. Okay? So I hope you appreciate the diversity in all these bulk properties, masses, radii, temperatures. Not only that, even their orbital parameters are extremely diverse. I've shown you a beautiful orrery here by the Kepler team. The star is not in this picture. All the blobs you're seeing are planets. The star is the center point, okay? So there are all kinds of orbits out there of exoplanets. And there are planets, there are systems that are extremely compact. For example, 6 planets sitting inside the orbit of Mercury in the solar system. Okay, so extremely compact, and all sorts of eccentricities, inclinations, and so forth. So again, exoplanets are extremely diverse in every conceivable way, every way you can think of. And not just that, there are planets out there which have no analogs in the solar system. I've told you about hot Jupiter, Jupiter being extremely close to the Sun. So exoplanets are detected by various methods, a radial velocity transit method, like the transit of Mercury that you saw or didn't see yesterday. And then direct imaging, you just directly image the planet if you have good enough contrast. And then, so there are various planets shown here in the mass and semi-major axis scale. And then the solar system planets are shown for reference here. So planets that are conducive for atmospheric characterization fall in 2 categories, mostly, either the transiting planets or the directly imaged planets. So those are the 2 groups of planets for which the best observations to date have been possible. There are other kinds of atmospheric observations that are still in progress. And in today's talk, I'm only going to touch upon the transiting planets, just in the interest of time, okay? Because those are the planets that have seen the most progress in this area. A transiting planet is basically a planet whose orbital orientation is just right so that you, the observer, can infer the planet passing in front of the star. How do you do that? When you just look at the star, you're seeing constant brightness of the star. When the planet passes in front, you see a dip. And then the planet goes behind, the day side comes into view, you're seeing light from the planet. When the planet goes behind, you see another small dip, because now the day side flux from the planet is subtracted. So remember the 2 dips you saw, right? Now let's go to a cartoon of that. So that's the primary transit. When the planet is going in front of the star, the size of that dip is just this radius, the area ratio squared. Okay, the radius of the planet or the radius of the star squared. That's just the ratio of the areas. Now, at secondary eclipse, there is another little dip that you saw in the movie. The depth of that little dip is just this. It's the radius ratio squared, now weighted by the flux from the planet or the flux from the star. Okay, the B is just the Planck function to keep it simple. Now, to give you a sense of what the numbers look like, if we take a Jupiter-like planet, RP is 1 Jupiter, around a sun-like star, 1 solar radius, and calculate what this depth should be, that's it. So a Jupiter is a tenth of a solar radius. Okay, so that depth is 100th. So the transit depth, the primary transit depth, is 1%. So you could already tell what I mean is that just to detect the planet going in front of the star, you need a precision that's better than 1%. Okay, maybe 0.1% if you want a 10 sigma result. Now, if you put in the same numbers here and put some standard temperatures, let's say 2000 Kelvin and 6000 for the star, 2000 Kelvin for the planet because it's hot, and 6000 for the star, the numbers you get are according 10,000. which means to measure the atmosphere, the flux from the atmosphere of the planet, day side of the atmosphere of the planet, you need precisions that are much better than a part in 10,000. So these are the kind of observations we are talking about. We need extremely high precision observations. Now, let me show you some data. Now, a key point here is just from these relations, you see that larger and hotter planets have larger atmospheric signals. Now, here is a spectrum called a transmission spectrum when the planet is going in front of the star, right? So the expression for the baseline transit depth is RP or R star squared. Okay? So that's the baseline flux. But if you want the atmosphere, what you want is perturbations on top of that baseline measure, which is due to that small annulus, that blue annulus that you're seeing here. That's a further 1% effect. Okay? So this amplitude, this is a spectrum obtained with the Hubble Space Telescope of a hot Jupiter in transit. The amplitude of this, if you can read these axes, is of the order a part in 10,000. So now you see, if you want to detect the feature, a molecular feature in a transmission spectrum, you want precisions, photometric precisions, better per bin, better than a part in 10,000, better than 100 parts per million. If you want a really good signal, you want few tenths of parts per million. That's tough. Okay, that's very, very tough. And that's what we are dealing with here. And there are other data sets of thermal emission as well, and the precisions required are similar. So these are some of the best data sets, and we'll come back to this again. Now, you could do this at all wavelengths across the electromagnetic spectrum, from UV to visible and infrared, and there is various science you can gain from different wavelength bands. But I'm going to focus only on the infrared measurements in the rest of my talk, just in the interest of time, and because that's what is most important for chemistry. Question is, how do you go from this data set to the chemical abundance of the atmosphere of the planet? Okay, so let's look at that. So early observations in exoplanetary spectra, these were happening while I was a PhD student. And the observations we used to have were something like this. Now, don't mistake the solid curve for the data. The solid curve is the model, and the data sets we had at the time were just 3 points with large error bars. And there were claims of water with data sets like that just because the model went through the data points. Now, we all know here that's not a robust detection to claim, because if you double the error bars, you can fit, or like even increase them by 50%, you'll fit them with a flat line. Okay? So the question, when I was a graduate student, the question that was on everyone's mind was, how do you solve this degeneracy problem? Because there could be many models that go through these data points. So how do you tell which is a unique model, and how do you extract the chemical information from the spectrum? So that was the focus of my thesis, and one of the things that was mentioned in the citations. So the way we solved that problem was as follows. Now you see, in each of these cases, there were only a few data points, but the number of free parameters in the models are more than 10. Okay, there were a large number of free parameters. So the question reduces to how can you parameterize an atmospheric model efficiently and run it efficiently so that you could convert this into a standard parameter estimation problem. Okay. In all areas of astronomy, we have parameter estimation problems. We want to convert this problem into that same framework. And the way we did it is as follows. Bear with me. This is a slide. The next two slides are slightly complicated as far as the numerics are concerned. So this is a standard atmospheric model, just so you know. It has all the standard equations of hydrostatic, equilibrium, radiative transfer, energy transport, and equation of state, and so forth. And then there is a chemical model, and then there are various boundary conditions, free parameters, and so forth. Now, the key innovation that went into solving this problem was to realize where the crux of the matter is, where the free parameters are. We realized very quickly that it's the opacity, and it's obvious in hindsight, but the opacity has basically, this is where the chemistry goes in the molecular abundances of each of those species, and we figured that if we can parameterize the chemical abundances, we've solved part of the problem. And then we also had to solve the temperature profiles. So this is the parameterization for the temperature profile, and we assume several free parameters, so on and so forth. I won't go into the details. The details are here. But basically, we reduced a complicated atmospheric model into one with several free parameters that can run very fast on a cluster, on a computer cluster. It has various advantages. It's computationally fast, can explore the parameter space and so forth. And this was one of the first papers where we did this. It's pretty crude. Based on just 6 data points, we could constrain temperature profiles. This is temperature, that's pressure. We could constrain temperature profiles, and each color now is showing a degree of fit to the data. You could come up with contours in parameter space and so forth. What it also allowed us to do in later work is, for the first time, we were able to put constraints just from 7 or 8 these photometric data points. We could put constraints. These are, by the way, Bayesian posterior probability distributions in the various molecular parameters. What we could do is basically put statistical constraints on the various key molecules in the atmosphere, and from that we could put constraints on the elemental abundance ratios in these atmospheres. So that was a big deal at that point. That was that paper, Nature paper, where we measured the first C2O ratio in an exoplanet. Now, I'm going to go fast in the remaining slides, just go through various data sets that have come up in recent times. So the retrieval techniques are pretty common now. Between 2009 and now, several groups have replicated the techniques, and this is one of the recent results where we can go from each of these data sets, convert these into molecular abundance estimates, especially of water vapor in these atmospheres, using the Hubble Space Telescope infrared and near-infrared observations. So you could see the best measurement here is HD 209458, and there the error bar on the data is about 20 parts per million. But when you convert that to molecular composition, we also get an error bar on the molecular composition in the atmosphere, which is also of the order tens of parts per million. Now, you can imagine the intensity of the situation, right? You're never seeing the planet. You're just seeing that dip in the starlight. And from that, you're able to not only infer the presence of chemicals in the planet's atmosphere, but you're also able to tell how much of that chemical is in the planet's atmosphere. Now, that's a huge leap in our understanding of these things, in remote sensing of exoplanetary atmospheres. And I'm going to show you one of the majestic data sets. Again, this is a hot Jupiter in high definition. So these are all derived from observations. This is real data-based spectra. As the planet's day side comes into view, you see the spectrum going up because the planet's day side is heated. And then when the night side comes into view, you see when the day side is coming into view, the spectrum is increasing in intensity. And when the night side comes into view, the spectrum is going down. Okay? Now, this is for an exoplanet, using lots of HST time. This is with 60 HST orbits, which is a lot of time. But we are able to map the surface temperature distribution of an exoplanet as it's going around its orbit. Now, this is a big deal. Okay? This is one of the biggest results in the field. This was Stevenson et al., my colleague. This was a science paper. And I'm not going to go into the details, but this is the phase curve that you get. This is the transit. This is the secondary eclipse depth, that little dip you saw in the movie. And I'm not even plotting here the main transit depth, which is of the order of percent. Okay, this is of the order a part in 10 to the 4. Yeah. From those kinds of observations, you can also get the spectra with very high precision detections of water vapor. Okay. Now, we are pushing, as I said, the smaller you go, the lower you go in size and temperature, the harder it's going to become to detect their atmospheric features. This is for a Neptune-sized planet. I told you, I mentioned to you how a Neptune is just 4 times Earth's radius, and here we are just about detecting the Neptune, the water vapor in this atmosphere at only about 3 or 4 sigma confidence. Now, we also, people, not my group, but other groups have also tried to do this for super Earths, this is an example of a super Earth at about 2.7 times Earth radius, again putting 60 HST orbit, but just looking at the transit of the planet over and over again, and this is the result we get. The error bars, you see, this is the spectrum, and this is the most expensive flat spectrum in the history of astronomy. So you could fit a flat horizontal line through all the data. Okay, so that's how hard it is to measure atmospheric features of super Earths. Okay, so I'm almost running out of time here, so I'll just conclude my talk in just a couple of minutes to give you a sense of what's happening now. Right? So I've taken you through two major leaps in our understanding. I've taken you through how we detect these features at extremely high precision, and then I've spoken about how we convert those high precision observations into high precision molecular abundance estimates. Now the third major revolution that's happening right now is reconstructing the planet's historical past based on these chemical abundance measurements. Okay? How do we do that? This is Jupiter in the solar system. We have measured, for Jupiter, we have measured several of these elements and their abundance relative to hydrogen, relative to sun. So most of these elements are enhanced by a factor of 2 or 3, okay, relative to solar abundance. And that has been used as evidence for core accretion of planetesimals when the planet was forming. Okay, you need to accrete a lot of rocks and solids, solid ices to increase these elemental abundances. But the key is, for Jupiter, we still don't know what the oxygen abundance is. Now, this might sound like a conundrum, a confusion to you. How do we measure water in exoplanets? And now I'm telling you that we don't know the oxygen abundance in Jupiter, in the solar system. The key is actually quite simple in hindsight. There is a mission called Juno that's going to Jupiter right now, and it will reach there in July this year to measure water abundance. Now, the reason we don't know Jupiter's water abundance is as follows. I'm showing you pressure temperature profiles, that's pressure, this is temperature again, of all the giant planets in the solar system, and that's the water condensation curve. The solar system giant planets are extremely cold, 100 degree Kelvin, so all the water vapor is frozen in their atmospheres. Okay? So you have to send a probe into the planet or use microwave measurements to get water vapor. But for hot Jupiters, hot exoplanets, that's not a problem, because they're 2000 Kelvin hot, or even 3000 Kelvin hot. All the water is in vapor form, and hence spectroscopically accessible even from our own space-based telescopes. So this is one of the biggest revolutions in our understanding that we have had recently, is that for once we can measure something better in an exoplanet's atmosphere than in atmospheres of our own solar system planets. Okay, so that's a big deal. So oxygen and carbon to oxygen ratios are better measured in exoplanets. So we go from that, and I showed you this plot already as proof of concept, and now we are using that to reconstruct exoplanetary formation mechanisms. Now, the key logic here is that planets form in disks around stars, and as you go from the center of the system to outside, the composition in the disk is changing as a function of time and space, okay, as time and location. So if you form a planet at a given time and a given location, and it's coming to its present location, the elemental abundance from its accretion history should be preserved. That's the principle on which we are operating. So if we can measure the elemental abundances and the abundance ratios in an exoplanet atmosphere, we should be, in principle, be able to reconstruct the past of the planet. That's a long shot. It's a very complicated chain of steps. And we are using that to infer the formation and the origins of hot Jupiters. This cartoon, which is as you go outside in the disk, you hit various ice lines of various molecules, and hence the carbon to oxygen ratio in the disk is changing, both in the gas and in the solids. And if you form planets at different locations and migrate them to their current locations by various means, what you end up with is a transformation from their formation pathways to their current chemical footprint in terms of the carbon and oxygen ratio. This is a recent paper where we first proposed this idea in 2014 on how you can construct formation and migration of exoplanets by making these observations. So with the future outlook of the field. Okay, so I've taken you through a very fast trip of all that's happening, but what is happening now and in the recent past, but what is the future? As of this year, we have also made a few key breakthroughs of observing small planets. This is the first detection of variability of thermal emission varying as a function of time for a super Earth. There is this first evidence, tentative evidence. Don't take this too seriously. Tentative evidence for volcanism on a super Earth. You can read all these papers if you're interested in. We have also measured, this is the most recent Nature paper just from last month, where we have for the first time measured a thermal phase curve of a super Earth, a rocky planet around another star. Now, this is a huge leap in our ability to measure atmospheres of these things. And we also know, as I mentioned at the beginning of my talk, we also know about the existence of several habitable planets out there. So the future is to be able to identify planets in their habitable zones by one measure or another and be able to do atmospheric spectroscopy on those. Where you can summarize the future of exoplanet science into two broad regions. One is to find smaller and smaller planets around nearby stars. Nearby stars is not because we want to get there anytime soon. Nearby because the closer the star, the better the precision you can get on the stellar flux, and hence the better the precision on your atmospheric observations. Okay, so we want small planets around nearby stars, and then we want to be able to characterize the atmospheres and interiors of these objects with spectroscopic measurements like the ones that I showed you. And there are various missions that are underway, in many of which we are involved. NGTS, several of these are run from Cambridge or have a big Cambridge participation. There is a NASA mission called TESS. There is an ESA mission called CHAOPS. These are both these are all space-based missions except for NGTS, which is a ground-based survey. And then there are several other ground-based surveys that are happening to detect these planets. And then for characterizing the atmospheres of these planets, there are many more facilities coming as well. The James Webb Space Telescope, as you all know, is going to be the next major breakthrough in space telescope capabilities. We'll have that for detailed observations of exoplanet spectra, and then we'll have the large ground-based telescopes like the TMTs and the ELTs of the future that will enable us to make these major developments. So this is really the golden age of exoplanet science, and I hope you're all enthused enough that we'll have a big participation from our country here in exoplanet science in the coming future. Thank you.